Let's have a look at the graphs of exponential functions. Here are the two basic views that you can have of an exponential. We say one is increasing, as you can see the one on the left here, and one is decreasing. Later on we'll talk about growth and decay and doing some problem solving there. I like to say, imagine that you have to walk along each of these graphs, and so the one on the left, if you're a little person and you're walking along that, it's like a hill, isn't it? And so think about how steep that hill is. Unlike the linear equations and functions that we've been working on, which were straight lines, the steepness of those stays the same the whole way along, whereas these, have a look at, if that was a hill, how fast that increases. And we say that increases exponentially. That's its growth. From an equation point of view, here it is up here. It's a y equals function, noting that the x, the variable, is in the power for exponentials, and a is always the y-intercept. So the number being multiplied by the base, you'll know straight away that that a number is the y-intercept. So that'll come in really handy. Also worth noting that b determines the direction. So here are the two versions that can happen. If the b number is greater than 1, so it could be 1.1, 1.2, or it could be 20, 30, 100, you can instantly know that the graph is one of these uphill functions. If the b value is between 0 and 1, so it might be 0.1, 0.2, or it might be things like a half or 2 on 5, something like that, it's going to be decreasing, so it's a downhill function. That b value also helps us to determine the rate at which the y values are increasing. So this comes in really handy when we do problem solving questions. So for example, if the b value was 1.23, you might be familiar with that from different topics, like some financial maths topics, where it's a multiplier. So if we're multiplying something by 1.23, we're actually increasing it by 23%, which means for every 1 unit that we go across in the x value, so on your x-axis or in a table of values, the y value is increasing each time by 23%. As you can see, that's why these graphs get so high and tall so quickly. And the decreasing functions, now this is not decreasing by 89%, it's the difference down from 100. So 100 subtract 11 would give you that 89, so it's decreasing by 11% for every time the x unit increases by 1. This will probably make a bit more sense when we start to put it into practice. Just some things to consider here for our notes. If we have the function y is equal to 2 to the power of x, if you were to construct a table of values, what's happening? Our x values are going up by 1 each time. What's happening to the y value? That would be where the function here where we have x is -3, that's essentially we're working out y is equal to 2 to the power of -3, and that's how we get that 1 on 8. This one here is y is equal to 2 to the power of 0. Anything to the power of 0 is 1, and that gives us our y-intercept at 1. Possibly worth noting that this equation is also 1 multiplied by 2 to the power of x. So there's always a number being multiplied by the base, but if it's 1, we tend not to write it. What's happening to the y values each time here? As you can see, they're increasing, and they're increasing by a factor of 2. That table of values matches the graph over to the right then, noticing that we've put dots for every number in the table of values, and that will help us plot it. Just some little side notes here. Some of the language that you may or may not need is the idea of an asymptote. And so let's have a read of what it's got here. As x tends towards -infinity, so that's going off to the left, y tends towards 0 from above. So y is getting really, really, really close to 0, but it's never going to touch it. And it's coming down from above to get close to that 0. And that's the formal way we write that. We don't tend to use this much in general mathematics at year 11, but it's worth knowing it. And we say that, therefore, y is equal to 2 to the power of x is asymptotic to the x-axis, or y is equal to 0 is a horizontal asymptote. So an asymptote is a line that you can't see because it's just where the graph is getting really, really, really close to, but it's never going to touch or cut. Well, in this case, sometimes they do cross them, but it's talking about its behavior is asymptotic. So that's a new word for you. A couple of examples just to demonstrate asymptotes. If we have this example here, y is equal to 2 times by 1.2 to the power of x. Things to start remembering. This number that it's being multiplied by, the 2, that's always your y-intercept. So start remembering that really quickly. And then 1.2, that's a number greater than 1, so it will be increasing, and hence the shape of the graph here. Now I've just put plus 0 here. This number at the end here is the asymptote number, which is y is equal to 0. It's the sort of an imaginary line that the graph's getting really close to without touching. What about a different example? This graph, it's the same, the three graphs I'm showing you are the same here, but just the number on the end changes. So yes, this is the y-intercept number, except the graph has now been vertically shifted up, translated up 5. So if we started at 2 for our y-intercept here and we add on 5, what number do we end up at? 7, and that matches. That's our new y-intercept at 7. And also this asymptote idea. It looks like the graph is heading towards y is equal to 5, but not touching it. And so that's what that asymptote looks like. What about if it's a subtract number? This one here, same first part of the graph. The y-intercept would be 2, which is here. However, the whole graph has been shifted down 2, hence that subtract 2. So now our y-intercept is at 0. But what about that asymptote? Can't quite see it on the graph, but you can imagine then a horizontal line at y is equal to -2, that one there, and that's the asymptote. Comparing the three all next to each other, you can see that algebraically how similar that they are in the format that they're written, and it's just the addition or subtraction number that's the end, and that's the number that shifts the graph up or down. Now, in the work that you'll be doing, you'll be asked to sketch graphs like this. So how do you go about sketching that? First thing to note, the y-intercept. What is that value? We can read that straight off and say that it's 2. So when we come to graph this, we'll know to put a dot at 2, and that's where the graph's going to cut through the y-axis. Now, how else do you do this? There are multiple ways. Finding the x-intercept can be helpful. Then you've got 2 points, but we tend to need at least 3 to plot a graph. We've got the y-intercept as 1. You could do a table of values, and you might have 5 or 6 values. That takes a little bit of time. One technique to suggest is doing 2 x values the same distance apart. So what if we did x is 2 and x is -2 and find the y values at that point, plot them and see what we get. So I'm going to write out what I said. We're going to do x is equal to 2 and x is equal to -2. And so we're going to substitute that into the formula. So we have y is equal to 2 multiplied by 1 on 3 to the power of 2. Obviously, I'm getting that equation from the bottom of the screen there. Feel free to just type that into your run mode and work that out. But just in case you're interested in the algebra to go with that, that's 2 multiplied by 1 on 9, which leaves us with 2 on 9. So 2/9. It's quite a small number. What's that as a coordinate? X is 2 and y is 2 on 9. What about when x is equal to -2? Same idea, substitute in -2 where you see an x. So we get 2 multiplied by 1 on 3 to the power of -2. Again, feel free to use your calculator to do that. The simplification is 2 multiplied by 3 squared. That's how the negative power works, which is 2 multiplied by 9, which gives us 18. And that as a coordinate is -2, 18. So let's think about our graph here. X values we've got from -2 to 2, and the y values we've got 2 on 9, 2 and 18. We don't have any negative y values. So approximately our graph, let's draw something like this. Putting in some x values, the scale doesn't need to be the same on the x and the y. And now we need 2 for the y-intercept, but then we also got to 18. So I'm actually going to count up by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18. Of course, this is much better done on grid paper. Label your axes, put arrows on them. So where did I get to? So there was 2, 4, 6, 8, 10, 12, 18. That's just the top one. Let's put some dots on. The y-intercept is at 2 there. Then when x is equal to -2, we're all the way up at 18. And then another value is 2, 2/9. So that's really small. So I'm going to put that really close to the x-axis there. Then we connect the dots. Trying to think about the shape that you're going to draw there that you've seen in those previous graphs. It needs to have a bit of a curve. I'll attempt that. So there's my approximate curve. Don't have it pass over that x-axis there, which is that horizontal asymptote. Do put arrows either end, and it's really good mathematical etiquette to label your graph, so give it its name there. Obviously don't have it cross over. And here's one that's written much nicely, can't even speak now, more neatly. There it is from the textbook there. That's the rough shape that we have. Notice that we've got the y-intercept of 2, using these 2 values here, putting dots, and then connecting the dots and giving it a label. So that's what you would roughly do when you have to sketch a graph. I'd like to briefly take you through two other ideas to help you answer some of the questions that I'm sure you'll get in your textbooks. What if you're asked to identify a graph, and here is the equation, which is the same as y is equal to 2 multiplied by 3 to the power of x. That little dot in between there is another way of writing multiply. Which one is it? This number here we know is the y-intercept. Well, they've all got 2 as the y-intercept, so it could be any of them. Now, how do you work out the next bit? Each of them are increasing exponential functions, so that this number here, the base, will all be numbers greater than 1. Which one's the 3? One technique then is to substitute in a value. So when x is equal to 1, what should it be? In this case, it's y is equal to 2 multiplied by 3 to the power of 1, which is 2 times 3, therefore y is 6. So which graph has the coordinate 1, 6? So when x is 1 and we're up at 6 for the y, it's B. So the graph that matches that equation is B. And lastly here, just to compare what some of these equations would look like and how they change. There's 3 that are increasing. What would their equations be? Let's do the dark green one there. First of all, what are their y-intercepts? They're all at 1, which would mean they're all, when you do it in this form, the 1 is in that place of the a, so it's 1 multiplied by b to the power of x. As we've mentioned before, if it's multiplied by 1, you actually don't have to put that in. So these 4 functions will all have this format, just y is equal to b to the power of x. What are the 4 b's then? Well, there are numbers on those graphs that will help us. So the dark green one here is y is equal to 10 to the power of x. The dark blue one here is y is equal to 2 to the power of x. This e number that you see here is actually a bit of a special number. You know how pi represents a number? E represents a number 2, and the number that it represents is 2.718 approximately. It's an irrational number, so the numbers don't end or repeat. And so what do you notice here? When this one was 2, and then the e is 2.718, and then up to 10. What do you notice about the steepness of these graphs as that base number increases? They're getting steeper. So that's just something to remember here. And this half, the equation for that would be a half to the power of x. And notice that that's a little bit shallower, but also a decreasing graph. These questions match 13C. Thanks for joining me. And probably worth noting that all of the asymptotes in these questions are 0, so you don't have to worry about asymptotes. It was more me something just bringing it to your attention. Thank you.